There is no question that Korean electric vehicle battery makers have established themselves as major players in the market in recent years, and they are now thinking big and targeting China, the rising market for EVs.
60 years into the race for longer-lasting electric car batteries, a fresh twist may change the rules. We have heard of new batteries with faster charging, yet nothing promises the kind of endurance just shared by a team in South Korea. Their secret lies in one perfect crystal grain that stands up to heat, pressure, and repeated charging. Soon we may hear of cars that run for lifetimes on a single set of cells. What is behind this breakthrough? But what if you could erase those weak spots completely? No cracks, no decay, just pure uninterrupted power, cycle after cycle. Could one flawless crystal finally unlock the Holy Grail of batteries? What makes this battery different? Electric cars today rely on batteries built from many small crystals pressed together. Each of those tiny grains can crack or wear out as drivers charge and discharge their cars. Cracks let air and moisture seep in, which harms performance over time. The team at the Korea Advanced Institute of Science and Technology chose a fresh path. They grew one single, flawless grain of nickel-rich material instead of dozens of separate pieces. With only one crystal, there are no grain boundaries to split or weaken under stress. In a typical battery, engineers mix nickel, manganese, and cobalt oxides into a powder. They press that powder into pellets or sheets and sinter it at high heat. During sintering, many crystals form and meet at borders. Those borders are weak spots. When a car charges at a fast rate, lithium ions flow quickly through the material and push against those borders, causing tiny cracks. Over hundreds of cycles, those cracks multiply, reducing how much energy the cell can hold. By contrast, a single crystal cathode has no borders inside the crystal. All atoms align in one continuous lattice. That means stress from lithium-ion movement spreads evenly instead of concentrating at the edges. The Korea Advanced Institute of Science and Technology Group heats its powder above 850 degrees Celsius in a tightly controlled furnace. At that temperature, atoms move just enough to fuse into one large grain. Gas flows through the chamber to keep oxygen levels steady. After hours of careful heating and cooling, they slice the block into thin sheets ready for cell assembly. The cathode sheet is mostly nickel oxide mixed with small shares of manganese and cobalt. Nickel drives up the voltage and energy density. Manganese stabilizes the crystal when the cell heats up. Cobalt adds safety by slowing down unwanted chemical reactions. This accurate blend delivers high power while keeping the structure strong. When lithium ions shuttle between the cathode and the anode, they enter and leave the crystal smoothly. That smooth flow avoids the tiny cracks that plague patchwork cathodes. In lab tests, these single crystal cells retain over 95% of their initial capacity even after 3,000 full charge cycles. If one cycle gives a car 500 kilometers of range, 3,000 cycles translate to 1,500,000 kilometers on paper. Real-world driving varies, but these numbers point to more than 1 million kilometers without swapping cells. Most electric vehicles today need a new battery pack after 200,000 to 300,000 kilometers. This new design could stretch that by 3 to 5 times. Driving without frequent battery swaps has real benefits. Owners save on spare parts and labor. Fleets such as taxis and delivery vans cut downtime when packs last much longer. Even drivers who keep the same car for a decade may never see capacity fall below 80%. That steady performance helps drivers plan long trips without worrying that range will suddenly drop. Old fears about hidden damage in a used electric vehicle pack could fade as packs promise reliable lifespans. Beyond drivers, the planet gains when cells last longer. Mining for lithium, nickel, and cobalt uses vast amounts of water and energy. Rivers can dry up near lithium mines, and mountaintops can be stripped away for nickel ore. Each battery swap demands new raw materials. Longer-lasting cells mean fewer swaps and less mining. In places already under strain from metal extraction, that relief can protect ecosystems and water supplies. Adopting single crystal cathodes also fits into current factory lines. Cell makers already install furnaces and dryers when they update plants. Adding a precise sintering step and high-temperature control costs more power, but engineers are exploring heat recovery and faster cycles to cut waste. The rest of the process, which includes mixing powder, coating sheets, and rolling or stacking cells, stays the same. That makes it easier for companies worldwide to test and scale the design. But here's the twist. What if solving the battery crisis doesn't start with some flashy new invention, but with something almost invisible? A microscopic change that could shift the future of energy. How do you build a battery so precise that it can survive the planet's biggest challenges? How they make it. Making a single crystal battery begins with choosing very pure raw materials. Engineers measure nickel, manganese, and cobalt compounds on an accuracy scale. They pick grades with minimal impurities so the final crystal stays strong. After weighing, they mix these powders with a small amount of binder. The binder helps the particles hold together when they later form into a solid block. Next, they add just enough water to turn the dry mix into a smooth paste. This paste must be uniform, so every particle shares the same composition. Once the slurry is ready, technicians pour it into shallow trays. They let the trays sit in a warm room until most of the water evaporates. As moisture leaves, the paste turns back into fine powder. Workers then scrape up the powder and sift it to break up any clumps. This sieving step ensures the grain size stays consistent. Consistent grain size is vital for uniform heating later. If some grains are much larger than others, the crystal could grow unevenly and develop weak spots. The heart of the process is sintering, a method of fusing powder into a solid mass with heat. The team at Korea Advanced Institute of Science and Technology uses a custom furnace that can reach beyond 850 degrees Celsius. They load the sifted powder into high-grade ceramic crucibles. Inside the furnace, an inert gas flows steadily to keep oxygen levels just right. Too much oxygen can cause the crystal to oxidize unevenly. Too little can leave tiny air pockets in the grain. Maintaining gas flow and temperature within tight limits takes careful monitoring and automated controls. Over a 12-hour cycle, the powder slowly densifies into one large grain. At first, particles stick at their contact points. As heat soaks in, atoms migrate and fill in gaps. Boundaries between original particles disappear. By the end of the cycle, the mass behaves like a single crystal. Engineers then drop the furnace temperature in stages. Rapid cooling can cause stress cracks, so they let the block cool over several hours. This slow cool-down preserves the crystal's integrity and prevents fractures. When the block is fully cool, technicians remove it from the furnace and inspect its surface. They look for any signs of cracks or discoloration. Next, they use a diamond-coated saw to slice the crystal block into thin sheets. Each sheet is a future cathode plate. Workers polish the edges to remove rough spots. Clean edges help maintain good contact when cells are assembled later. After cutting, each plate passes through a scanner that checks thickness and flatness. Plates that fall outside strict tolerances get recycled back into the powder mix. The prepared plates move on to cell assembly. First, each cathode sheet receives a thin coating of conductive carbon and polymer binder. Once that layer dries, the sheet goes into a roll-to-roll machine. There, it meets an anode sheet made of graphite. A polymer separator film sits between the two sheets to prevent direct contact. All three layers roll up together and slip into a protective pouch or metal case. Technicians inject a liquid electrolyte that carries lithium ions during charging and discharging. The final pouch seals shut under heat and pressure. To test quality, the team runs each cell through a series of checks. They measure electrical resistance, capacity and self-discharge rate. They charge and discharge each cell under controlled conditions to confirm it meets performance targets. Cells with even a small deviation get flagged for further inspection. Those who pass enter a longer test where they repeat charge cycles hundreds of times. Cells showing any abnormal fading get pulled from the batch. Only the best reach the million-kilometer claim. Scaling this method from lab prototypes to factory output poses challenges. Lab furnaces handle small batches, but car makers need tons of cathode material every day. Building large-scale sintering ovens with the same precision takes time and investment. Engineers explore ways to cut energy use during sintering. Some propose capturing and reusing waste heat. Others test faster temperature ramps to shorten cycle time without harming crystal quality. Despite extra steps, the single crystal approach can fit into existing battery lines. Most producers already have mixers, dryers, coaters, and roll-to-roll machines. They only need to add high-temperature furnaces and gas controllers for sintering. Many plans to pilot small production lines before a full upgrade. Early partners include major cell makers such as LG Energy Solution and SK On. If pilot runs prove cost-effective, large-scale factories may adopt the process within 2 to 3 years. By using one flawless grain, the process removes weak points inside the cathode. The rest of the assembly follows familiar steps. This synergy speeds adoption and keeps costs from soaring. The next challenge is balancing the extra furnace power against longer cell life. As the process moves from the lab to line, engineers will refine details such as furnace size, gas flow rates, and cooling profiles. Each tweak brings the million-kilometer battery closer to real-world roads. But building a better battery in theory is one thing. Proving it on the road is another. What happens when these flawless crystals leave the lab and face the chaos of reality? How far can it go? Scientists measure battery life not just by hours on a charger, but by how many times a cell can charge and discharge before its capacity drops. In early tests, the single crystal cells keep over 95% of their capacity after 3,000 full cycles. If each cycle gives an electric car a 500-kilometer range, then the math points to 1,500,000 kilometers on paper. Actual driving conditions vary, but even cautious estimates suggest these cells could power cars for more than 1,000,000 kilometers without major loss in performance. Turning lab results into real road data requires field trials. The Korea Advanced Institute of Science and Technology team has shared prototype cells with Hyundai Motor Company and LG Energy Solution for testing inside real car packs. Engineers build modules with dozens of single crystal cells and install them in test vehicles. They drive on highway loops, urban streets, and mountain roads. Every few weeks, data logs record capacity, temperature, and internal resistance. These logs help technicians spot early signs of wear, such as slow loss of charge or rising heat under load. High-speed charging puts extra stress on cells. To see if the crystal holds up, testers charge cells at twice the normal current. Rapid charging can heat cells above 45 degrees Celsius. In these stress tests, the single crystal cathodes show capacity fade rates that are half those of standard polycrystalline cells. That means drivers could use fast public chargers more often without worrying about early battery wear. Extreme temperatures also affect battery life. In summer trials, cars run in desert heat above 50 degrees Celsius. Conventional cells lose capacity faster under those conditions. The single crystal cells heat more evenly and resist cracking under heat stress. In winter trials, test cars drive on snowy roads and sudden cold snaps below minus 20 degrees Celsius. While capacity dips at very low temperatures, cells recover strength once warmed inside the pack. Grain boundaries in polycrystalline cathodes often crack in freezing weather, but the solid crystal here stays intact. Mountain and high-altitude tests add another layer. Thin air and cooler temperatures make it harder for packs to shed heat. Test drives over mountain passes as high as 3,000 meters help engineers see how pressure and temperature swings affect performance. The single crystal design maintains stable voltage over long climbs and descents, with only a small decline after thousands of kilometers. Computer models now speed development. Simulations of ion paths in a crystal guide tweaks in composition and heating. Manufacturers plan warranties covering 1 million kilometers to reduce buyer risk. Comparing single crystal cells to today's batteries highlights the gains. Most electric vehicle packs lose 20 to 30% of capacity after 1,000 cycles. That drop shows up as less range and slower acceleration. Single crystal packs keep the range steady much longer, and their internal resistance rises more slowly. Drivers feel consistent power and range, even after years on the road. Fleet operators often drive cars harder than private owners. Taxis, delivery vans, and rideshare vehicles can clock 200 kilometers per day. A driver might replace a pack every 2 to 3 years. With single crystal cells, operators could stretch that life to 6 or more years. Lower maintenance and replacement costs make electric fleets more profitable and reduce downtime. For private owners, the resale market changes if packs stay healthy longer. Used electric vehicle values depend on how much battery life remains. A car with an original pack still at 90% capacity sells for a premium. With single crystal cells, owners might never see capacity below 80%, even after a decade of use. That confidence could boost demand for used electric vehicles and keep resale prices stable. Heavy vehicles benefit too. Electric buses, trucks, and construction machines often need pack overhauls at midlife. Single crystal technology could let those vehicles complete their full service life on one battery set. Fewer pack changes cut downtime and labor. At the same time, reduced scrap cuts, waste, and recycling costs. This 1 million kilometer promise depends on scaling from prototypes to factory output. Engineers must prove that every cell off the line meets the same high standards. As trials move from hundreds of cells to thousands, data will show if the crystal method delivers at scale. Early signs point to a future where electric vehicle owners track total kilometers with ease, knowing their pack can last a lifetime. But here's the real test. What happens when this technology leaves the lab and hits the streets? Can it truly reshape not just resale values, but how we live with our cars every day? What it means for drivers and the planet. For drivers, a battery that keeps its strength past 1 million kilometers changes daily life. No one needs to park at a service center just to trade cells. Most people drive between 30 and 50 kilometers a day. Today's packs often need replacement after 200,000 to 300,000 kilometers. With a single crystal design, that interval stretches to 10 times longer. Drivers save money on parts and labor. They spend less time waiting at repair shops. Lease and rental companies can offer simpler plans with fewer swap fees. Car makers can promise long warranties without setting aside huge reserves. Budgets shift from pack care to features that drivers enjoy. Mining for lithium, nickel, and cobalt often strains water supplies and land. In arid zones, pulling 1 ton of lithium from salt flats can use over 2 million liters of water. Nearby streams run low, and local villages feel the loss. Nickel mining can clear forests to reach ore, leaving scars on hillsides. Cobalt sometimes comes from small-scale mines with mixed safety records. When batteries wear out after a few years, many metals go for recycling or to landfills. Recycling recovers only 80 to 90% of each metal. That gap grows over decades. If cells last 3 to 5 times longer, the total need for raw materials drops by the same factor across markets. Cell makers worldwide watch this method closely. Companies such as LG Energy Solution, SK On, and Samsung SDI have pilot lines. They mix crystal powder in existing coaters and dryers. Next, they feed it through a high-temperature furnace, like the one at Kest. Factory engineers measure electric performance after sintering and slicing. They log energy use for each batch. Each pilot run helps them adjust furnace size, gas flow, and cooling time. In some plants, they test capturing furnace heat to warm dryer rooms. Others try faster heating ramps. These small tweaks bring the lab process into high-volume factories. Fleet operators value long-life batteries. Delivery vans and taxis cover 100 to 200 kilometers a day. With standard packs, they plan a battery service every 2 years. Single crystal cells could stretch that to 5 or 6 years. Spot checks in maintenance yards change from cell swaps to wiring and cooling system work. Mechanics spend less time on pack swaps and more time on other repairs. Fewer battery changes cut spare parts storage needs. Companies save on labor and lower the total cost of ownership. Financing terms may improve when lenders see less risk from battery swaps. They track energy use per route. For private buyers, a long-lasting battery lifts resale value. A used electric vehicle often trades at 70 to 80% of its new price when the pack still holds 80% capacity. Buyers worry about hidden damage inside the cells. Single crystal packs promise stable wear and clear health reports. Owners could show decades of solid performance with little fade. That openness may push resale prices higher across markets. Dealers might advertise cars with packs rated for 500,000 kilometers or more. Certified pre-owned programs could cover longer periods. Banks and insurers may offer better rates if they see strong pack health. The used electric vehicle market may grow faster as trust in battery life rises. Used battery packs enter recycling streams when they fail performance checks. Current recycling can recover 80 to 90% of metals like lithium, cobalt, and nickel. The rest ends up as waste or low-grade scrap. Over time, that loss adds a burden. Single crystal cells that last longer cut the flow of spent packs by 2/3. Fewer spent cells mean recyclers can handle less volume. They may sort materials carefully and reduce energy per recycled ton. Waste from damaged cells drops sharply. That shrinkage in waste streams lowers costs for recycling firms. As car makers adopt crystal technology, the total scrap volume may fall enough to change recycling economics. That change can improve margins for recycling plants and reduce fees. This isn't just a better battery, it's a shift in how we think about time, value, and the planet itself. If one crystal can power a car for 1,000,000 kilometers, what else could it change?